In today's video, we will consider vector-valued functions of one variable. Note that so far we considered scalar-valued functions of several variables. Okay? But in our three-dimensional world, we have a lot of vector-valued functions. So, from a point of view of physics, it is also essential in all applications to consider such functions. This will not be yet in full generality because we will not be considering vector-valued functions of several variables, but just one variable at this stage. So, well, we recall that we talked about such functions, namely that a function from R into R squared, okay, had its graph in R3, and the graph was a curve. In space. Okay, now if we generalize this a little bit, that is, but of course, if f is from R into R3, then the graph But of course, since the graph is in R4, we cannot visualize it. But especially in applications, we can consider the domain variable as time t, okay? And then we concentrate on the range. So physically, this gives us a point, that's the position, moving in time. We then interpret this as a point, okay, moving in space. Okay. So this way, just by looking at the range, okay, for a fixed t, okay, we can then obtain a curve. But of course, because there is a t, and we interpreted that as time, okay, this movement has a speed. Actually, because it's a vector, a velocity. Okay. Then, okay, this, okay, moving point, okay, has a velocity which we can describe as follows. Okay. We are in space and we have okay, a curve C, and we have a point moving on it. Okay. This, of course, means that we have a movement from P to this point, that is P of t to P of t plus delta t, but these are vectors. And so, okay, we consider two vectors here. Well, maybe my curve will be a little bit better looking. So let me check it as follows. Let's say this is my point. And so we end up with two vectors. One is P of t vector, the other one is P of t plus delta t vector. Then, of course, the difference of them, that is P of t, P of t plus delta t vector in between, okay, is the difference vector here, which is P of t plus delta t minus P of t. Okay. Now, because this is a position vector, okay, and the derivative of the position is defined in physics as velocity, then the velocity will be the derivative of P of t. Okay, let me call it as velocity. This would be the limit t going to, well, let me say at t0, t going to t0, P of t minus P of t0 divided by t minus t0. Now, all this operation is possible, of course, because these are, after all, vectors, but we divide by a scalar. So it is well defined. Okay. Now, this vector, P of t plus delta t minus P of t, as we can already observe from the picture, okay, as delta t goes to 0, will approach a vector which is directly tangent to the curve at t0. Okay. Well, we already used this approach quite a lot. Okay. But now let us make the formal definitions. Namely, this is the limit t going to t0 of x of t, y of t, and z of t minus x of t0, y of t0, z of t0 divided by t minus t0. Okay. So what we used so far was just consider the derivatives of the components. Actually, this is a definition. Namely, limit of a vector function is limit of x of t, of course the components, t minus t0, limit of y of t minus y of t0 over t minus t0, and limit of z of t minus z of t0 divided by t minus t0. In other words, it is nothing but the derivatives So what we're saying here is that if we have a vector valued function and if we want to differentiate it, we differentiate it term-wisely. So differentiation, which we did not consider here, but also integration is defined termwise. Okay. So for a vector valued function, we can consider termwise differentiation and integration. Okay, we applied it to three-dimensional vectors, but of course you can do the same thing for two component vectors, as well as vectors with higher dimensions, and so on. Okay. Now, again, going back to physics, we defined this derivative vector as the velocity vector, but actually we had already called it the tangent vector before. So, okay, as a note, mathematically, okay, this v of t vector is called the tangent vector. Okay. Okay, as before. So we already considered this, but now we are looking at the problem from the point of view of physics. Well, of course, one can likewise consider the derivative of the velocity vector. Well, this simply means the second derivative of x of t, y of t, and z of t. If you have two dimensions, just take the first two. Well, by definition, okay, the derivative of the velocity is acceleration. Well, the last thing I will say here is that all the product rules in vector valued functions are the same as in the one variable case. So let me just remark, I will not prove these, it's very easy to show it. Okay. The product rule is valid for vector valued functions as well. Okay. Namely, if you take the derivative of a scalar valued function times a vector valued function, say this is something like p of t, q of t, and r of t, okay, then what do you expect to get? You multiply them first. This is scalar, this is a vector, and then take the derivatives. Of course, what you have is the derivative of f times f of t plus f of t times the derivative of the vector valued function. Okay. If you multiply it with a scalar. But the same argument is valid if you multiply, okay, two vector valued functions. That means, of course, as a dot product or cross product. So if you multiply two vector valued functions, okay, in a dot product fashion, okay, what you get, of course, is the derivative of the first one dot, because this is a vector now, the second one plus the first one dot derivative of the second one. The usual product rule is valid. Okay, the same is true if you take the derivative of a cross product. Because these are vector valued, all of these operations are valid, and this will be exactly the same thing as that one. That is f prime t cross, this time, g of t plus f of t cross g prime of t. This, of course, is a vector. Right. So these operations are valid as in the usual product rule that we have. Okay. Now, to apply these ideas, we started with physics. So, as an example, okay, let us consider the following. Okay. Let an object, some mass, okay, move, okay, in a circle due to a centripetal force. That means an inward force, okay, which is constant. Okay. So the situation is something like this. We have a circle, okay. We have a point. It's moving this way, say some m, and okay, there's a force which pulls it. Okay. This is the force F. Okay. Well, a centripetal force pulls the object, okay? But because the movement is on the circle, it's always perpendicular to the trajectory of the motion. So we have here the tangent line is perpendicular all the time. Okay. Now let us analyze this motion. Well, you can regard this as planetary motion. For example, this is the moon, and at the center we have Earth. Okay, it pulls it, all right, but always in a perpendicular angle. So what does all this tell us? Okay, let's make it more look like a circle. Well, clearly then, okay, by Newton's law, actually second law of motion, okay, this force in question is ma. Of course, a is the vector here. The mass is, well, it's a scalar. It doesn't change. We are not in the speed of light, so m is constant. We are in Newtonian physics. Well, this means that this is the derivative of velocity, as we already considered. But because of the perpendicularity and the velocity vector is in the tangent line direction, okay, we have by perpendicularity that F is perpendicular to V at any time. Well, we assumed the force is constant, okay? So the this means, of course, that the length of the vector is constant. Okay. We assumed, let me emphasize, that norm f is f, it's constant. Okay. Now this perpendicularity can be used as follows. Let us consider the length of the vector v squared. Okay. Now this length is, by our vector knowledge, v of t dot v of t. And the derivative as we said, it's the derivative of the dot product. So obeys the product rule, which is, by the way, the derivative of the first times the second one. These are all dot products, plus the first one dot the derivative of the second one. Okay. Well, this is the vector A. In fact, because the dot product is commutative, that you can change the places of the vectors in a dot product and nothing will change, this is 2 times the derivative vector dot the velocity vector. Okay. Both of them depend on t. Well, we just said that the force is perpendicular to v, but the force is a scalar multiple of the acceleration. And so this is 0 since f is perpendicular to v. Okay. But what does this tell us? Well, the derivative of a function of one variable and scalar, because we have the norm here. Okay. This scalar valued one variable function of real numbers has a derivative which is 0 for all t. Well, this means that this function, okay, must be a constant. Okay. Well, of course. So the length of the velocity is a constant. Well, what do we conclude from here? Well, we conclude that if you have a centripetal force, that is a force perpendicular all the time to the trajectory of motion, then okay, its velocity does not increase nor decrease. It's constant. So okay, we conclude that okay, any f okay, which is perpendicular to the trajectory or the direction of motion okay. But of course, okay, here we assume f is constant. Okay. Well, I will tell in a minute why we assume that. Okay. This does not change the velocity, hence the kinetic energy. So, okay, if you apply a force perpendicular to the direction of motion, okay, that does not change okay, the kinetic energy. It does not add energy to the system. Well, of course, this explains, okay, why the moon does not fall into Earth. Actually, this explanation is very crude. I mean, you cannot describe the motion of the moon just with a simple argument as this, but this is the essence of the argument. This is the main argument. Okay. Actually, astronomers tell us that, or physicists tell us that eventually they will fall in a few billion years, whatever. And of course, the moon does not go around the Earth in a perfect circle as well. But more or less, that is the explanation one can give. Well, following this idea, which can be attributed to physics, because we talked about accelerations and velocities, okay, but we can give this approach a more geometric meaning. Okay. Namely, let us consider curves. Well, how do we define a curve? Well, we already know some examples. For example, we already talked about that x of t, y of t was a curve, or as in this physical interpretation, if you look at the range of the function and consider t as time, okay, we have a curve and we have a body moving on it with speed or velocity, the derivative, and so on. A more formal definition will be given here. So let me directly give the definition, because we already considered this a lot of times. Okay. Well, the range of a continuous function okay, say alpha, from an interval into r squared or r3 or, okay, r to the n. But we will be considering only these in our arguments, okay, where I is an interval. Okay, this can be R itself. It's called a curve. Okay, if you have the range R2, you will have a curve in plane. If you have a curve in R3, you will have a curve in space. Okay, this way or the other, we are talking about the range of such a function, not the graph. So we should be careful about this. Well, now let me give you some examples. But before doing that, let me emphasize one thing. Okay, the range of such a function, well, is a curve, could be half a circle, for instance. Yes, but there are other functions which give the same range. The functions are not unique here, because we only consider the range. Okay, so, okay, since, okay, many, actually infinitely many, okay, such functions can give the same curve, that's the range, okay, say C, okay. These functions which give this C certainly are not unique, and so okay, each of them is called a representation or a parametrization of C. So we have a geometric figure in R2, for instance, and it's the range of some function. There can be infinitely many such functions. Each of them is called a representation or a parametrization. This is the more mathematical term. Okay. Now let us consider some examples of curves. Okay, a very standard example is, for instance, okay, the function of one variable. Well, because the range will be a vector, usually we put an arrow here, but it's not that necessary. Suppose it's cosine t and sine t. Okay. Note that the domain, the interval, must be specified because it changed the curve at the end. So we will say that t belongs to 0 to pi. Now, clearly this is a function into R2, okay? It's a curve, right? But let us be more geometrical in our approach. What does all this say? It says that the first one is our x, actually depending on t. The second one is our y. Well, the sum of their squares is always 1. So, okay, we get okay, a unit circle. So this is our curve C. And this is a representation for it. Now let us consider an alpha, which is the same, but this time t starts from 0, but ends at pi. Well, the same argument holds, namely x squared plus y squared is 1 again. So it's a circle, all right, a unit circle, but, okay, t does not cover all points on the circle. Namely, we have the following. Okay. When we are at the 0 position, we are at 1, 0 here. We have a circle, all right. Okay. But when t increases, clearly here, okay, for every point xy, t represents the angle from the geometry directly. And when the angle t increases from 0 towards pi, clearly cosine t decreases but positive, sine t increases and positive. So actually we are moving this way. But we stop when t is pi. So this is C. So it's the upper half circle. Or we can consider a different function, which is t and square root 1 minus t squared. And t changed from minus 1 to 1. Now what does this tell us? Well, again, when t is minus 1, x is -1, and y is 0. So this is the case when t is -1. Well, again, if this is our x, this is our y, okay, squaring them and adding them, we get 1 all the time. So this is likewise a unit circle. Okay. However, we stop when t is 1. Clearly, when t increases from -1 towards 0, okay, the first component in length decreases, but the second one increases. So y increases, x decreases. We are moving in this fashion, and we stop when t is equal to +1 at the point 1, 0, which corresponds to t is 1. Of course, somewhere in between here, okay, t will be, what will that be? 0. Okay. So we will have the point 0, 1 at this point. Here, t is 0. It increases from -1 towards 1. It passes through 0. Well, this is the same c. So both, okay, this alpha and this beta represent the same curve. So both alpha in 2 and beta, okay, represent the same curve C. So there can be many representations of the same curve. Okay, continuing with more examples. Let me consider like my third example, I suppose. Maybe fourth. Okay. Okay. So let me say it's the fourth one. Okay, consider the curve described by this function as t squared, and t is in R. Okay. What do we get, of course? Clearly, this is our x, this is our y, so y is x squared. And x changed from, that's t, minus infinity to plus infinity. So this curve is the parabola, okay? Y is x squared. So this is our c. So a curve need not have endpoints all the time. Well, this is the graph of the function x squared. So c is the graph of f, where f of x is x squared. Okay. Well, we have a general name for such cases. Let me just put that right away. Okay. If alpha is t f of t, okay, for some, of course, continuous f from R to R, then we call this parametrization the trivial one. Namely, you just put, instead of y, f of t, well, it's the graph of f. Okay? Since C is the graph of f. Okay. So that's a standard term we will use all the time. Well, in this case, then, of course, let us note that, okay, a beta, something like t cubed and t to the 6, t running in R. This is not the trivial parametrization for this f, because we have t cubed, but it's just another parametrization. For the same curve, which is the graph of f that we considered for x squared. Okay. But, for example, a gamma t, which is t squared t to the 4th, t in R, is not a representation or a parametrization for the same curve. But for the following curve. Well, okay, what's the difference? Well, here we have x and y. Y is equal to x squared all the time, so it's the parabola, all right. Okay. But x is never negative. It's t squared. So it's a parametrization for this one. So by playing with the domain or with the powers, you can get part of a curve, you can visualize it and characterize it in many ways. Okay, let us have an example in 3 space. It's important to understand what parametrization means, because we will be using it in line integrals quite extensively. Okay, consider a function now as, say, t minus 2, 2t plus 1, and, okay, 2t plus 5. And t changed from minus infinity to infinity. Clearly, this representation gives us a curve in space, because we have 3 components, okay? And we recognize it in a very simple way. That is, this is our x, this is our y, and this is our z. And all of them are represented in terms of t's, where we don't have any squares or anything. So this is actually a parametric formulation of a straight line in space. Okay. So, okay, alpha represents a line in space, okay, whose parametric form is x is t minus 2, y is 2t plus 1, and z is 2t plus 5. Okay. Well, as a still different example, let us consider again some 3-dimensional curve with cosine t, sine t, and 1, where t runs from 0 to 2 pi. Now this is almost the same as our planar curve, namely our x and y satisfy x squared plus y squared is equal to 1. So it's a unit circle again. But z is 1. And this is a curve in space. So again, we have a unit circle, but z is always 1. So it's not on the xy plane, it's on the plane z is equal to 1. So this tells us that we have something like this. Here we have, okay, a unit circle. So this is, it is a unit circle, okay, hanging in the air above the xy plane. Okay. At the level z equal to 1. Now let us change this even a little bit more. Let us consider a curve which is cosine t, sine t, and t. Okay. And t, say, changed from 0 to, well, rather, let me change it, Now, what do we have here? Well, from the geometry, x is cosine t, y is sine t. Well, together, they say that, okay, x squared plus y squared is always 1. But in space, this is a cylinder. So, okay, because we're in space now, we have 3 components. So, we have then the following. Okay, we have a cylinder. Oh, well, sides should be parallel, of course. And the radius is 1. So, the curve is wound around the circle. Okay? It has a winding effect going around the cylinder all the time. Because x squared plus y squared is 1, it's on the cylinder. However, okay, let us start with this xy plane. Okay, when t is 0, well, we are at the point 1, 0, 0. Now, when t increases, as in the two-dimensional case, our point goes around the cylinder. That is, around a circle. But at the same time, t increases. So, okay, the point goes around and around, but at the same time, you push it up. So, we would have something as follows. The same thing goes below as well. Okay? Namely, you go down, it goes up and down, and so on. So what do you get? Like a wire, okay, wound around, okay, a stick. So it's called a helix, a spiral, actually, but a very special spiral. Okay? So it is such a curve in space. Now, so far, we saw a lot of examples of curves in space or in plane considered as the range of continuous functions on intervals all the time. Okay. Now, let us try to assign a direction to the curves we have. Okay. These will be directed curves. So I will give the title directed, but actually a more common term is the orientation. So it is oriented curves. Well, clearly, whether in space or in plane, there are two orientations you can assign to a curve. So, clearly, there are two orientations, or if you want, senses, okay, that can be assigned to a curve. Namely, okay, let me give an example from plane. Okay. Say you have such a curve, and you have the same curve. It's the same C. Okay. But this goes like that, and that means, of course, this one, or the opposite. Okay. Well, in this sense, they are oppositely oriented, so they are not the same curves, if you consider them as oriented curves. If you forget orientation, well, they are exactly the same. Okay? So this is the same C, but of course, orientations differ. So they are not the same. Well, how do we know that a curve has a certain orientation, this or that? Of course, we cannot know. If we only know just this figure of the curve without these arrows, then we don't know which orientation is meant. In other words, the orientation must be given. Okay, if we want to talk about an oriented curve, there must be an orientation assigned to it. Okay, this orientation must be given, okay, together with the curve. Well, this means automatically that, okay, all representations of a curve certainly would not give the same orientation. Okay, let me talk about these as remarks and definitions. Okay, first of all, if we don't have an orientation, it's not given, but okay, a particular representation is given. That is, some function giving this curve is given. Then the orientation is taken to be okay, in the increasing direction. Okay, we are given a representation, so we have a function, and when t increases, how does the orientation go? we can directly see it geometrically. So this is a default if a representation is given. If it's not given, certainly you cannot know which orientation is meant. Okay. Well, when we talk about orientations, of course, because we have two of them, a special name can be given to the other one. Okay. Well, let C be an oriented curve. That's a curve with a direction. Okay. So the orientation is given. Okay. Then we show, okay, C with the opposite direction by minus. Well, so you have a C and you have an orientation. If you change the orientation, you show it by minus C directly. Well, that minus sign there is not just a symbol that we put there to show the opposite orientation, but it will have some meaning as well with respect to the integrals that we will define later. Okay. And okay, we can add two curves, two oriented curves, if the endpoint of one is the starting point of the other one. Okay. And orientations match. Okay. What do we mean by that? Let me give you some examples directly. For example, in R2, okay, say this is a curve C1 with this orientation. It's an oriented curve. Then, of course, the same curve with the opposite orientation would be called minus C1. It's certainly understood. And now, okay, if we have a curve C1 and another curve C2, but with the orientations continuing in the correct direction, then this whole thing is called C1 plus C. Okay. But on the other hand, okay, say we have this C1 and we have this C2, but with the opposite orientation. Now, what do we have in this case? Well, of course, I can write this as two curves where this one is C1 and this one, which is minus C2. And so this is actually C1 minus C2. So this way, we have an algebra of curves. Well, one convention maybe is important here. Let me just say that if a closed curve, actually closeness is not enough here. I should define a simple curve. Okay, if a closed curve, which does not intersect itself, is not oriented, by default, counterclockwise direction is assigned to it. This is a convention. That is an agreement. Okay, we agree that if you have a closed curve which does not intersect itself, but there is no orientation, okay, the counterclockwise orientation is automatically assigned to it. Well, two more concepts about curves, maybe here. Well, further definitions actually. A curve is called closed. Actually, I used it there, but I'm defining it right now. Okay. If the interval is a closed interval, and there is actually all representations, and we have alpha of A equal to alpha of B. Okay. Well, if you start from one point, you go around the curve and come to the same point at the end, you call it a closed curve as expected. For example, the circle, okay, is a closed curve, or a curve of this form is closed, okay? But of course, if you cut it somewhere, it will not be closed, it's obvious. Now, okay, a curve is simple if there exists a parametrization which is one-to-one. Now, what does this mean? Well, for different t's, you never have the same point. Well, that means the curve does not intersect itself. Okay, but we have one exception. If C is closed, okay, then, okay, and does not intersect itself except at, okay, A and B, then it's also called simple. So, okay, this curve, this is simple, closed. Okay. This curve, okay, is closed, but not simple. Okay. Such a curve clearly is not simple, and of course not closed. Okay. And well, yes, so these are the basic examples that we have. Well, the last definition in this video or a curve is smooth if it has a parametrization with differentiable components. With differentiable component functions. Okay. Well, usually it's required that at no point the derivative will be 0. And for all t, okay, the tangent vector is different from the 0 vector. Okay, so this is a smooth curve. And finally, it's called piecewise smooth. Okay. If it is a sum of finitely many smooth curves. Okay. So, for example, okay, a circle is smooth with an orientation. Okay. Of course, here I didn't say it explicitly, but okay, we don't require anything at the end points because that's not feasible. Of course, we require one-sided derivatives to exist. But that's understood, so I will not say more on it. Okay, and of course, a curve like this is piecewise smooth.